Right now, in the world's most advanced laboratories, physicists run experiments. These experiments could shatter everything that you thought was real. Buried deep in quantum mechanics, something strange has been found. It is hidden within the mathematics of black holes. It is encoded into the very fabric of space-time itself. Scientists have discovered something that seems impossible. They have found evidence that our universe might not be what we think. The stars, the planets, and even your own body could be stranger. They could be a projection, a hologram, or a simulation. In 1974, Stephen Hawking made a discovery. His discovery effectively broke the known laws of physics. He proved that black holes are not eternal objects. They slowly evaporate over immense periods of time. They leak a faint radiation until they vanish completely. This sounds harmless enough on the surface, but it created an impossible problem that still haunts science. Here is why this matters directly to you. Everything in our universe follows one single iron law. Information can never be destroyed, not ever. When you burn a book, its information is not truly gone. It still exists in the particles of smoke and ash. It exists in the heat that is released into space. Physics demands a form of perfect bookkeeping, but black holes seem to violate this fundamental rule. When matter falls into a black hole, its information disappears. It vanishes behind the mysterious event horizon. The event horizon is the boundary where nothing can escape. Then the black hole evaporates through Hawking radiation. This radiation is completely random in its nature. It carries no information about what fell into the black hole. The information simply vanishes from the universe forever. Einstein's general relativity said that this was fine. Quantum mechanics, however, said that this was impossible. Two of the most successful theories in history were at war. Both of them could not possibly be right. Physicists went searching for a solution to this paradox. What they found was even stranger than the problem itself. In 1993, a Dutch physicist proposed something radical. His name was Gerard, a Nobel laureate. What if the information never really fell inside the black hole? What if it stayed on the surface the entire time, encoded on the event horizon like data on a hard drive? This is now a confirmed theory in modern physics. Leonard Susskind developed this idea even further. He showed that everything inside a black hole could be described. It could be described by information on its two-dimensional surface. This is just like a three-dimensional hologram. A hologram looks completely three-dimensional to our eyes, but all the information creating that image lives on a flat surface. The apparent depth of the image is just an illusion. Here comes the part that changes everything for us. If this holographic principle works for black holes, why would it not also work for the entire universe? Think about what this strange idea actually means. Every single atom that makes up your body, every star that is burning across the vastness of space, every single thought that you have in your mind, all of it might be information encoded on a distant boundary, a cosmic event horizon that is trillions of miles away. We think that we live in 3 dimensions of space. We think that we are moving through a real physical space, but we could just be projections from somewhere else. Holographic images created by data existing somewhere else entirely. This is not some kind of wild science fiction. This is the holographic principle, a leading theory in physics. Scientists have run computer simulations to test this idea. In 2013, a Japanese physicist did a calculation. Yoshifumi Hyakutake calculated the internal energy of a black hole. He did this using the complex mathematics of string theory. Then he calculated the energy of a lower dimensional universe, a universe that had no gravity within it at all. The two numbers that he calculated matched perfectly. Juan Maldacena at Princeton called it a correct computation. The mathematics of the holographic principle works perfectly, but nobody expected what came next from this. When physicists looked closer at our own universe, they found evidence for this idea hiding everywhere. They found strange patterns that only make sense in a hologram, and that was just the very beginning of the problem. You are not where you think that you are right now. According to the holographic principle, your reality is a projection. The three-dimensional universe you experience is encoded elsewhere. It is encoded on a two-dimensional boundary infinitely far away. Everything that you see, touch, and feel is a projection. It is a projection from this very distant surface. This theory is currently unproven, but it is widely accepted. It is widely accepted among many theoretical physicists. It solves the black hole information paradox perfectly, but it also suggests something deeply unsettling about reality. Space itself might not be a fundamental aspect of the universe. Imagine that you are watching a movie on a screen. The characters in the movie seem to move through a three-dimensional space. They can walk forward and backward and up and down, but the actual information creating this scene lives on a flat screen. The apparent depth of the scene is manufactured by the projection. Our entire universe could work in the very same way. The holographic principle says that everything happening in a volume of space, it can be completely described by information on the boundary of that space. It is like a room where everything inside is determined by equations that are written on the walls of the room. This idea first emerged from the field of string theory. It emerged in the year 1997. Juan Maldacena discovered something truly remarkable. He proved that a five-dimensional universe with gravity, it could describe the exact same physics as a four-dimensional universe. A four-dimensional universe that had no gravity at all. Two completely different realities with the same underlying information. Physicists now call this the ADS, divided by CFT correspondence. The technical details of this do not really matter. What matters is that this idea works mathematically. Scientists have tested this correspondence thousands of times. The predictions that it makes have always matched. Mark van Ramsdonk at the University of British Columbia said it felt magical. It was like a revelation that appeared from absolutely nowhere. Suddenly, physicists could translate impossible gravity problems. They could translate them into solvable quantum problems. But here is what keeps many of the scientists awake at night. If our universe is holographic, then space itself is not real. The concept of distance is not a fundamental property. The vast gap between you and the nearest star is an illusion. It is created by the way information is organized on that distant boundary. Think about what you are doing at this very moment. You are reading these words and you are breathing the air. You are existing in what feels like real three-dimensional space. According to this theory, all of it is simply emergent. It is generated by something that is much simpler and flatter. You are an equation that is currently being computed. Recent studies have found even more evidence for this. In 2017, researchers published their findings. They published them in the journal Physical Review Letters. They showed substantial support for a holographic universe. They analyzed irregularities in the cosmic microwave background. This is the ancient afterglow of the Big Bang itself. The patterns that they found matched the holographic predictions. They matched just as well as they matched standard cosmology. Leonard Susskind at Stanford said, "These results confirmed something." Physicists were fairly sure that this had to be true. The thermodynamics of certain black holes can be reproduced. They can be reproduced from a lower dimensional universe. But our universe is not identical to the models they tested. The cosmos that we inhabit is what is known as de Sitter space. It is not the anti-de Sitter space used in the models. Scientists are still working toward a perfect match. If they are able to succeed in this endeavor, it will prove that our universe is truly a hologram. And once you accept that reality is just projected information, a much darker and more profound question begins to emerge. Information that is encoded by what or by whom? The mathematics of this has no answer for that question. In 2013, a team of Japanese physicists did something. They did something that should have been completely impossible. They calculated the properties of a black hole in two different ways. One of the ways used string theory in 10 dimensions, the other way used quantum mechanics in just 1 dimension. Two completely different universes with two different sets of physics. The results of the two calculations were identical. They were identical down to the very last decimal point. Every single property of the black hole matched perfectly. The internal energy, the entropy, and the position of the event horizon, even the effects of virtual particles popping in and out of existence. Juan Maldacena called it a correct and important computation. Leonard Susskind said it was the first numerical proof of something that physicists had believed but had never confirmed, that fundamentally different realities can be perfectly equivalent. This is hard experimental evidence, not just speculation. Yoshifumi Hyakutake led the research team at Ibaraki University. They used powerful supercomputers to simulate both universes. They simulated both of them at the very same time. The incredibly complex calculations took many years to complete. When the numbers finally came in, they revealed something profound. Two universes that appear to be nothing alike can describe the same system. It is like two different languages, translating the same sentence perfectly. But here is what makes this discovery so deeply disturbing. If completely different realities can produce identical results, how do we know which one of these realities we actually live in? We could be the inhabitants of the higher dimensional universe, the one that has gravity as a fundamental force, or we could be living in the lower dimensional universe without gravity. Both of these two different realities would feel exactly the same to us. The mathematics of this cannot tell the difference between them. Think about a character that exists inside of a video game. That character exists in a three-dimensional world from its perspective, but the actual code for that world runs on a processor somewhere else. The world that the character experiences is not where the computation happens. We could be the very same kind of being, experiencing a projected reality while the real computation occurs. It would be occurring in a totally different kind of space. Scientists have expanded these simulations since 2013. They have tested many other different configurations, different numbers of dimensions and different types of forces. Every single one of these tests confirms the same thing. The concept of holographic equivalence really works. Physicist Netta Engelhardt at MIT studies these dualities. She said that knowing you are talking about the same physics, talking about it from two different perspectives is incredibly powerful. Sometimes problems that are impossible to solve in one description, they can become completely trivial in the other description. Researchers have used this to study black hole evaporation. They have also used it to study quantum entanglement, and they have used it to study the nature of space-time itself. Every new discovery in this area strengthens the case for holography. But these simulations have also revealed something else, something that nobody at all had expected to find. The holographic universes that work so well mathematically are simpler. They are simpler than our own universe appears to be. They have fewer dimensions and much less complexity. It is like seeing a high-resolution image on a screen and then discovering it was generated from a much smaller file. This suggests that our universe might be compressing its information. It might be running on some kind of efficiency algorithm, minimizing its computational resources while maximizing its output. This is exactly how you would design a simulation that needs to run on limited hardware. The Japanese simulations proved that holographic universes are possible. They work perfectly in the realm of theoretical physics. Scientists are now looking for evidence that our universe is one, and the first clues have appeared in the most unexpected place, a number that should not exist at all in our universe. There is a number in physics that is so wrong it should have destroyed the universe. This number is known as the cosmological constant. It is the thing that controls how fast space itself is expanding. Right now, the universe is known to be accelerating outward. Galaxies are moving apart from each other faster and faster. The cosmological constant is what explains why this is happening. Scientists have measured its value very carefully. It is a tiny positive number that is almost zero but not quite. Then they tried to calculate what its value should be. They tried to calculate it using quantum field theory. The prediction that came back from this calculation was huge. It was 120 orders of magnitude too large. Let me put that number into perspective for you. Imagine you expected something to be 1 inch long. You measure it and find out it is actually 1,000 billion miles long. That is just how wrong the prediction for this number was. This is the single worst prediction in the entire history of physics. Physicists call it the cosmological constant problem. Some of them also call it the vacuum catastrophe. Either of these two names works just as well. This is because both of them capture the same impossible situation. Our very best theory of quantum mechanics predicts a universe that simply cannot exist in reality. If the cosmological constant were even close to the predicted value, space would be expanding so violently that atoms could never form. Stars would be completely impossible to form in such a universe. Galaxies would never have been able to exist at all. The universe would have ripped itself apart in less than a second. It would have done so after the moment of the Big Bang. But here we are, living in a stable universe. A universe with a cosmological constant so precisely balanced, it seems as if it must have been designed that way. Physicist Paul Davies has explained it in this way. The vacuum of space itself contains a great deal of energy. Quantum mechanics demands that this energy must exist. This vacuum energy should be accelerating the expansion of the universe. It should be doing so in a catastrophic fashion. But something else must also exist in the universe, a negative value that is almost exactly as large as the vacuum energy. The two of them seem to cancel each other out perfectly. This cancellation creates the tiny positive number that we observe. This requires a level of precision beyond anything we have ever seen. Here is where the problem gets even worse for the physicists. The cosmological constant also depends on two other universal constants, the gravitational constant and the weak force constant. If either of these two constants changed by just a tiny amount, by just 1 part in 10 to the power of 50, the delicate balance would be completely shattered. 1 part in 10 to the power of 50 is a number so small. It is so small that it completely defies our comprehension. It would be like balancing a pencil on its very sharp point and having it stay perfectly vertical for billions of years. And it is not just one single constant that is finely tuned. Multiple different constants had to land in impossibly narrow ranges. They had to do so at the very same time. Many physicists believe that this fine-tuning points to a multiverse, countless different universes with different physical constants. We just happen to exist in the rare one that works. This is a very popular theory, but it is completely unproven. Others think that it suggests that we live in a simulation. Programmers who are adjusting the parameters until they got a stable universe. This is also unproven, but it is disturbingly plausible. Here is what we know for certain about this number. The cosmological constant is a real and measured value. The theoretical predictions for it are also real. The impossible precision of the cancellation is also real. Something has forced our universe to have exactly the right value. The odds of this happening by pure chance are effectively zero. Either there is a deeper law of physics we have not discovered yet, or something has deliberately set these numbers to be what they are. The cosmological constant is not the only finely tuned value. There are dozens more of these constants in our universe. Each one of them is balanced on the very same knife edge. Our entire universe runs on 26 numbers that should not work. These are the fundamental constants of modern physics: the strength of gravity and the mass of an electron, the speed of light, and many others as well. Each one of them had to land in a very precise range, a range that allows for reality to be able to function. If you change any of them just slightly, the universe collapses. Physicist Fred Adams has studied what happens when you alter these constants. He has run many computer simulations of alternate universes that have different values for these constants. Almost all of them were completely dead on arrival. They had no stars, no planets, and no possibility of life. The standard model of particle physics contains 25 of these parameters. They are freely adjustable parameters in the model. General relativity adds one more of these parameters. That parameter is the cosmological constant itself. These numbers are not predicted by any deeper theory. They are just what they are, we have to measure them. But here is the fundamental problem with all of this. The range of the possible values for each of these constants is enormous. Some of them could theoretically be infinite in their value, yet every single one of them has landed in the narrow band where complex structures are able to exist. Let me show you exactly what I mean by this. The strong nuclear force is what holds atomic nuclei together. If it were just 5% stronger than it is, something called a diproton would become stable. This is a nucleus with 2 protons and no neutrons. This might sound completely harmless, but it would destroy everything. Hydrogen would be able to fuse so easily that the entire universe, it would burn through all of its fuel in just a few minutes. It would do so after the moment of the Big Bang. No hydrogen in the universe means that there is no water. Water is 2 hydrogen atoms and 1 oxygen atom. Without any hydrogen, water simply cannot exist. No oceans, no rain, and no possibility of life. Stars also need hydrogen in order to be able to burn. They fuse it gradually into heavier elements over billions of years. This slow burn is what creates a stable energy output. But with all of the hydrogen gone from the universe, the stars would either never form or they would burn out immediately. The entire universe would be completely sterile as a result. Now let us consider the opposite direction for this. What if the strong force were just 5% weaker? The element deuterium would become completely unstable. This is a nucleus with 1 proton and 1 neutron. It is the very first step in building the heavier elements. Stars fuse hydrogen into deuterium and then deuterium into helium. Then they fuse helium into carbon and so on up the periodic table. But if deuterium cannot hold itself together at all, this entire chain of element creation is broken. Stars would not be able to create anything heavier than hydrogen. The universe would be just one single element forever. No carbon, no oxygen, no iron, and no heavy atoms at all. Every single element that makes up your own body, it requires the strong force to be precisely where it is. Carbon is able to form because of a specific resonance in the strong nuclear force. A slight change in this, and carbon becomes impossible to create. Physicist Fred Hoyle famously predicted this carbon resonance. He predicted it long before it was ever discovered. He said that it had to exist, or life would be impossible. When experiments finally confirmed that it was real, Fred Hoyle was completely shaken by the discovery. He said that it looked like someone had monkeyed with the laws of physics. The strong force also determines the stability of nuclei. If it is too weak, all atomic nuclei would fall apart. If it is too strong, exotic particles would become common. Scientists at CERN study the strong force constantly. They smash particles together at nearly the speed of light. They do this to measure how the different quarks interact. Every single one of these experiments confirms the same thing. The strong force is exactly the strength it needs to be. Not approximately the right strength, but exactly the right strength. We are talking about a parameter that could have any value across an absolutely enormous range. Yet, it has landed precisely in the sweet spot where chemistry works, where stable elements are able to exist in the universe, where complexity itself is a possibility for us. If you change it by just a couple of percentage points, all of existence as we know it would come to an end. This is not the last of the finely tuned forces either. There are many others that are just as critical. And when you look at how they all work together, the the picture becomes even more unnerving for the scientists. A physicist at the University of Portsmouth believes he has found evidence that we are all living inside of a simulation. His name is Melvin Vopson, and his argument is intriguing. It centers on a new law that he has formulated. It is called the second law of infodynamics. This law is designed to describe how information behaves, and according to Vopson, the universe is optimizing its information. It is doing so in the same way that computer code does. Let me explain what this idea actually means. In the field of computer science, data compression is essential. Large files can be reduced in size without losing important data. This makes computer programs run much faster, and it makes them use much less of the available memory. Every video that you stream and every image that you download, it has been compressed in some way to make it smaller. Vopson has noticed something very strange about our universe. Information systems in nature seem to decrease in entropy over time. This is something that should not be able to happen. The second law of thermodynamics says that entropy always increases. Disorder in a system will always grow over time. Yet information systems seem to follow a different rule. They become more ordered, more efficient, and more compressed. He has tested this idea by studying mutation patterns. He studied them in viruses, specifically the SARS-CoV-2 virus. This is the virus that causes the disease COVID-19. The virus is known to mutate constantly as it replicates. According to traditional evolutionary theory, these mutations should be random, but Vopson has found a very distinct pattern in them. The mutations that he has studied were not random at all. They were optimizing the information entropy of the virus. They were making the genetic code more efficient. They were effectively compressing it over time. This is a published finding in the journal AIP Advances. The data shows a correlation between information and mutation, a correlation that should not exist if mutations are truly random. Think about what this strange finding actually implies. Biological systems seem to be behaving like software that is being actively debugged by a programmer. It is finding all of the inefficiencies and eliminating them. It is streamlining its own code to be more efficient. But viruses do not have any programmers to do this. They have no conscious intention to optimize themselves. Yet they are doing it anyway, all on their own. Vopson argues that this compression happens everywhere. In the field of atomic physics, the electrons arrange themselves. They arrange themselves to minimize their information entropy. In the field of cosmology, the universe expands. It expands without gaining or losing any of its heat. This requires that the total entropy must remain constant. Thermodynamics says that the entropy should be increasing, but Vopson proposes that another type of entropy exists. This is known as information entropy, and it is decreasing. It decreases to balance the increase in thermodynamic entropy. Now, here is where all of this connects to simulation theory. If you wanted to simulate a complex universe like our own, you would need an enormous amount of computational power, more power than might be available to you. So you would need to compress the data to make it work. You would have to optimize it and find mathematical shortcuts that produce the same results with less processing. This is exactly what the second law of infodynamics describes. A universe that is actively compressing its own information. It is doing so to reduce its overall computational load. Physicist Paul Davies has written about this very idea. He has noted that the universe seems to follow a certain path, the path of least computational action in all things. Nature always finds the most efficient solutions to problems. It finds the shortest routes and the minimal energy states. This principle appears in classical mechanics as the principle of least action. Particles always take the path that minimizes a quantity called action. It is one of the most fundamental rules in all of physics. But why would nature care so much about being efficient? Why does the universe consistently choose the least complicated option, unless it is running on a system that has limited resources? Vopson believes that his new law could prove something. It could prove that we are all living in a simulation, a universe that is actively compressing its own data. It is a universe that is designed to run on a computer. This is his own theory, and it remains unproven. It is also very controversial among other scientists. Many of them disagree with his final conclusions. They argue that information behavior can be explained in other ways. It can be explained without invoking the idea of simulations. But the data itself is not really in dispute. The universe does appear to be optimizing its own information. It does seem to be running on some kind of compression algorithms. Whether this proves that we are in a simulation or not, or if it reveals a deeper law of nature, is still unknown. Either way, something is managing the computational resources of our own reality, and this optimization becomes even more obvious. When you look at the concept of entropy itself, there is a law in physics that nothing is supposed to violate, except the universe seems to be violating it constantly. The second law of thermodynamics says that entropy always increases. Disorder in a system will always grow over time. You can never spontaneously organize a system from chaos, not without adding some energy from the outside. This is the reason why your room gets messy on its own, but it never seems to clean itself up for you. It is why ice will melt but water will not freeze, not without a refrigerator to remove the heat. Entropy is often called the arrow of time in physics. It always points in just one single direction toward chaos, but information entropy appears to point the opposite way. Melvin Vopson has documented this in his own research. He has found that information systems become more organized over time, more efficient and less random. This seems to violate everything that we know about thermodynamics, unless there is some kind of balancing act that is happening. Vopson proposes that as thermodynamic entropy increases, the information entropy of the system is decreasing. The two of them seem to balance each other out perfectly. This is what keeps the total entropy of the universe constant. This matches what we have observed in the cosmos. The universe is expanding without gaining or losing any heat. This should be impossible according to our current theories. The expansion of the universe should be generating entropy, but our measurements show the total entropy is staying level. Where is all of that missing entropy going? Vopson says that it is being converted into information order. The universe is reorganizing all of its data, while its physical state is becoming more disordered. It is like a computer that is defragmenting its own hard drive. It is doing this while the program continues to run. Here is where all of this becomes truly strange. This kind of balancing act is exactly what happens in simulations. When you are playing a video game on your computer, the graphics engine is constantly optimizing itself. It only renders the parts of the world that you can see. It compresses all of the textures to save memory. It reduces the polygon counts in all of the distant objects. The simulation is able to maintain its performance. It does this by decreasing its information complexity. It does this wherever it is possible to do so. Your computer has a limited amount of processing power. The game has to be able to run efficiently or it will crash. So the code is designed to minimize the computational load. If our universe is a simulation, it would face the same constraints. It would have limited processing power and limited memory. The system would need to be compressing its data constantly. It would do this just to be able to keep running. And that is exactly what we observe in our universe. Physicist John Barrow has studied this from a different angle. He has looked at the mathematical symmetries that are found in nature. Symmetry is a form of data compression in itself. Instead of storing information about every individual particle, nature simply stores the patterns and the rules that apply to groups. This is exactly how computer software is designed to work. Instead of defining every single pixel on the screen separately, You can just define a mathematical function to do it. The function will then generate all of the pixels automatically. This is a much more efficient way of doing things. Nature does this everywhere that we look in the universe. The physical laws themselves are a form of compressed information. The equation for gravity applies to every massive object. You do not need to have separate rules for each star and planet. One single equation is able to cover everything. These equations are all forms of compression algorithms. They can generate an infinite number of specific cases. They can do so from a finite number of general rules. The universe runs on elegant mathematics for a reason. Elegant mathematics is the most compressed form of information, but thermodynamics says that this should not be able to happen. Information should become less organized and more random over time. Yet the physical laws of our universe remain perfectly consistent. They are consistent across billions of light years of space, and they are consistent across billions of years of time. Something is actively maintaining the order in our universe. Scientists have different explanations for why this is. Some of them say that deeper physical principles must exist, principles that we have not yet been able to discover. These principles would naturally create the balance between information and thermodynamic entropy. Others say that the multiverse is what explains it. We just happen to exist in a universe where the laws balance correctly. Other universes in the multiverse have different sets of rules, and then there is the simulation theory to consider. The universe compresses its information because it is running on a computer with finite and limited resources available to it. The second law of infodynamics is real code optimization. It is happening in real time all around us. We cannot prove which of these explanations is correct yet, but the data keeps pointing in one single direction. The universe behaves just like optimized software, and nowhere is this more obvious than in quantum mechanics, where reality itself changes based on what you observe. This is the experiment that has broken our common sense. It is known as the double-slit experiment in physics. Thomas Young first performed this experiment with light. He did so way back in the year 1801. When physicists repeated it with electrons in the 20th century, they discovered something that was completely impossible. Particles are known to behave differently in this experiment. They behave differently depending on whether you are watching them. Here is the basic setup of this famous experiment. You fire electrons one at a time at a solid barrier, a barrier that has two narrow slits cut into it. Behind this barrier, there is a detection screen. You would expect the electrons to pass through one slit or the other, and then they would hit the screen right behind that slit. Instead of this, you get what is known as an interference pattern, alternating bands of high and low electron density. This particular pattern is impossible if electrons are just particles. It only makes sense if the electrons are also waves that are passing through both of the slits at the same time, and then they are interfering with themselves on the other side. But electrons are supposed to be particles, not waves. We fire them individually at the barrier in the experiment. We also detect them as individual points on the screen. They cannot be in two different places at the very same time, except that they can be, and they are in this experiment. When you do not measure which slit the electron passes through, it behaves just like a wave would in the same situation. It goes through both of the slits and creates interference. Now let us place a detector at the slits themselves, something that can record which path the electron actually takes. If you run the experiment again with this detector, the interference pattern will completely vanish from the screen. Suddenly the electrons start to behave just like particles. Each one of them passes through only one of the two slits. There is no interference at all in this case, just two solid bands on the screen right behind the slits. The simple act of observation has changed the final outcome. This is a confirmed and repeatable experimental result. Scientists have repeated this experiment thousands of times. They have done so with photons, electrons, and even atoms. Even large complex molecules have been used in it. The result is always the same no matter what you use. If you watch the particle, it acts like a particle. If you do not watch it, it acts like a wave. Richard Feynman called this the central mystery of quantum mechanics. He said that it contains everything strange about the quantum world. Everything is compressed into just one single demonstration. But the story gets even weirder than this much weirder. Scientists have tried leaving the detector in place, but they did not record the data from the detector. The detector still measures which slit the electron passes through, but nobody ever looks at the result of the measurement. There is no human observer involved in this case. The interference pattern returns to the screen. The electrons seem to know whether the information is being stored. If the measurement is recorded permanently, even if nobody watches, the electrons will act just like particles in the experiment. If the measurement happens but is not saved in any way, they will act just like waves in the experiment. This should not be possible according to our common sense. The electron has no awareness, and it is not conscious. How does it know whether a detector is recording the data? Some physicists invoke the Copenhagen interpretation to explain this. Observation is what collapses the wave function of the particle. Before the measurement, the electron exists in a superposition of all of its possible states at once. After the measurement, it becomes one single definite state. But this just raises another difficult question for us. What exactly counts as an observation in this context? Does it require a conscious observer to be present, or is any interaction with a measuring device enough? Experiments have suggested that consciousness is not required. Any permanent record of the electron's path is enough. It is enough to destroy the interference pattern. This could be a detector, a camera, or even air molecules that scatter differently based on the path. The common factor in all of this seems to be information. If information about the path of the particle exists anywhere, the wave function of that particle will collapse. This is confirmed by the theory of quantum decoherence. Particles will lose their wave-like properties over time. They do so when they become entangled with their environment. The environment itself acts as a kind of permanent record. But here is the truly disturbing part of this story. Some interpretations of quantum mechanics say something different. They say the particle does not have a definite path at all, not until you actually measure it in some way. The act of measurement does not reveal where the particle was. It is what determines where the particle was in the past. You are not just observing reality in this case. You are actively creating it with your own actions. And delayed choice experiments make this even more unsettling. In 1978, physicist John Wheeler proposed an experiment so strange that most people assumed it was just a thought experiment, something that would be impossible to actually perform. Then, in 2007, some scientists actually did it, and the results that they got were truly terrifying. Wheeler asked a very simple question about this. What if you could decide whether to measure a particle's path? What if you could do so after it had already passed through the slits? Could your future choice be able to affect the particle's past behavior? According to classical physics, this is complete nonsense. The past is supposed to be fixed and unchangeable. What has already happened has already happened. Your decision that you make now cannot change what occurred before. Quantum mechanics, however, says something very different. Alain Aspect and his team in France performed this experiment. They performed Wheeler's delayed choice experiment with single photons. They used what are known as beam splitters instead of slits. The setup allowed them to randomly decide something, whether to recombine the photons' paths or to leave them separate. Here is the critical part of this experiment. They made this decision after the photon had already passed. After it had passed the first of the beam splitters, after it should have already chosen how to behave, whether to behave as a wave or as a particle. If they recombined the paths, an interference pattern appeared. The photon had behaved just like a wave would have. It had passed through both of the paths simultaneously. If they left the paths separate, there was no interference. The photon had behaved just like a particle would have. It had taken only one of the two possible paths. Their future choice had determined the photon's past behavior. This is a confirmed experimental result that was published in Science. Andrew Truscott at Australian National University repeated this. He repeated this experiment in the year 2015. He used helium atoms instead of photons in his version. He used a quantum random number generator to ensure something. He ensured that the decision was truly unpredictable. The atom could not have known in advance which measurement would be performed. He got the very same result as the previous experiment. The measurement choice that was made after the atom had passed. It determined which path the atom had taken before the measurement. This forces us to accept one of two different conclusions. Either particles do not have definite properties until they are measured, even if that measurement happens retroactively in time, or information is able to travel backward in time. Neither of these two options makes any sense to us, but both of them are supported by the experimental evidence. Most physicists tend to favor the first of these explanations. The particle's path is completely undefined until the measurement. It exists in a quantum superposition of all possibilities. When you make the measurement, you collapse the superposition, and you retroactively define which path the particle took. But this implies that the past is not actually fixed. Events that have already occurred can be altered by your measurements, altered by measurements that you make much later in time. Reality is not a series of definite moments progressing forward. It is a probability cloud that only crystallizes when it is observed. You are not just moving through time in this case. You are actively collapsing the possibility space around you. This connects directly to the theory of a simulated universe. In a video game, the environment does not fully exist. It does not exist until you actually look at it. The code only renders what appears on the screen. If you step into a new room, the game will load that room's data. If you step back out, it may unload that data. The past is not stored permanently in the game's memory. Only the current state and the future possibilities exist. Our entire universe could work in the very same way. The past is not a massive database of every single event that has ever occurred in cosmic history. It is a compressed history that gets generated retroactively. It gets generated when you measure something in the present. This would explain the delayed choice experiments perfectly. The particle's path does not exist in the memory until you check. When you perform the measurement, the universe calculates the path. It calculates what path is consistent with all of the prior measurements, and it then assigns that path to the particle retroactively. This allows for maximum data compression and minimum computational load. But we are not yet done with the quantum strangeness. The next phenomenon is even harder to explain. Harder to explain without invoking something deeply weird about reality. Particles that are able to communicate faster than the speed of light. They can do this across the entire expanse of the universe. And they are able to do it completely instantaneously. Albert Einstein absolutely hated this particular idea. He called it spooky action at a distance in his writings. But it turns out that he was wrong about this. You can take two particles and link them together in a special way. Then you can separate them by millions of miles of space. If you measure one of the particles, the other one instantly knows. It instantly knows what has happened to its partner. This is the phenomenon of quantum entanglement. It is a real and confirmed aspect of our reality, and nobody really understands how it actually works. Here is what makes this seem so completely impossible. Information is not supposed to be able to travel faster than light. This is a fundamental and unbreakable rule of relativity. The speed of light is the universe's ultimate speed limit. Nothing in the universe is supposed to be able to exceed it. But entangled particles are able to communicate instantaneously. They can do so across any distance in the universe. You can measure one of them and the other one will respond immediately. It will respond not after a delay, but right at that moment. Einstein thought that this proved that quantum mechanics was incomplete. He thought there must be some hidden variables that we had not discovered, some deeper reality that would explain the connection. In 1964, physicist John Bell proved Einstein was wrong. He formulated an inequality that these hidden variable theories must satisfy. Then experiments were performed to test this inequality. Bell's inequality has been violated consistently and repeatedly. This is a confirmed and well-established experimental result. Hidden variables cannot explain the phenomenon of entanglement. The particles really do communicate faster than light, or they share their information in a way that transcends space and time. Let me give you a concrete example of this. You can create two entangled photons in a laboratory. You can then send one of them to a laboratory here on Earth, and you can send the other one to a laboratory on Mars. If you measure the polarization of the photon on Earth, the photon that is on Mars will instantly take the opposite polarization. It will do so before the light from Earth could possibly reach Mars, before any signal traveling at the speed of light could cross the distance. The two photons will behave as one single unified system. This is despite them being separated by millions of miles of space. It is like they are both reading the very same data file, or they are accessing the very same line of code. This is exactly how variables in computer programs are known to work. Two different parts of the code can reference the same memory address. If you change one of them, the other one will update automatically, not because information has traveled between them, but because they both point to the same location in the storage. Entangled particles might work in the very same way. They are not separate entities that are communicating across space. They are two different access points to the same underlying information. This idea fits perfectly with the holographic universe theory. If all of the information in our three-dimensional space is stored elsewhere, if it is stored on a two-dimensional boundary, then the concept of distance is just an illusion. The entangled particles appear to be far apart in our projected reality, but at the information level they are right next to each other. Physicist Mark van Ramsdonk has shown that entanglement is essential. It is essential for the very existence of space-time. In holographic theories, quantum entanglement between particles. It is what creates the geometry of space itself. If you remove all of the entanglement, space would disappear. This is a leading theory in the field of quantum gravity research. Space is not a fundamental property of the universe. It emerges from the entanglement patterns in the underlying information. Think about what this means for you right at this moment. The atoms in your own body are entangled with other particles. Particles that are scattered throughout the entire universe. Your past light cone includes everything that could have influenced you. Everything that has influenced you since the Big Bang. You are not a separate and isolated entity in the cosmos. You are a localized pattern in a universal web of quantum connections. And those connections are able to transcend all spatial distance. Scientists have tested entanglement at increasingly large scales. They have entangled photons across hundreds of miles. They have entangled thousands of atoms all at the same time. They are even planning experiments to test entanglement between Earth and satellites. Every single one of these tests confirms the same thing. Entanglement is a real instant and universal phenomenon. But the most disturbing application of entanglement is quantum teleportation. This is not some kind of science fiction, it is working technology. It is being developed by scientists right now. You cannot teleport matter, but you can teleport quantum states. You can take a particle here and measure its properties. Then you can use entanglement to transfer those exact properties. You can transfer them to a particle that is somewhere else. The original particle is destroyed in this process. the distant particle becomes identical to what the original was. The information has traveled, but the matter has not. Chinese scientists have successfully teleported quantum states. They have teleported them to a satellite that is in orbit. European teams are now working on building quantum networks that will span entire continents in the future. This only makes sense if information is more fundamental than matter, if particles are not physical objects, but are information patterns. And if reality is just information, then there is nothing stopping it. Nothing is stopping it from being pure mathematics. This brings us to one of the most radical theories in physics. Max Tegmark is a physicist who works at MIT. He has proposed something that most scientists consider to be insane. He says that the universe is not just described by mathematics. He says that the universe actually is mathematics. Physical reality and mathematical structure are the very same thing. What we experience as matter and energy are actually just equations. Equations that are being computed by some system. This is called the mathematical universe hypothesis. And a disturbing amount of evidence seems to support it. Think about everything that we know in the field of physics. Every law, every force, and every single particle. All of it is described by mathematics with perfect precision, not approximately, but exactly, and without any exceptions. Newton's laws of motion are a set of equations. Maxwell's equations are what describe electromagnetism. Einstein's field equations are what explain gravity. Quantum mechanics is a purely mathematical formalism. But here is what Max Tegmark has noticed about all of this. We do not just describe nature with our mathematics. Nature itself seems to obey mathematics without any exception. No physical law has ever been found that cannot be expressed mathematically. Why would the universe follow mathematical rules so perfectly, unless the universe itself is fundamentally mathematical? Tegmark's argument goes even deeper than this. He says that if a mathematical structure exists, it has a physical existence. Every possible arrangement of numbers and every consistent set of equations. It corresponds to a real universe that is somewhere out there. This is what he calls the level 4 multiverse. It is a multiverse that contains every mathematically possible reality. Our own universe is just one single solution to one set of equations. Critics of this idea have called it completely absurd. They say that mathematics is a human invention, just a tool that we have created to be able to describe nature. It does not exist independently of our own minds. Tegmark, however, disagrees with this point of view. He points out that mathematical truths are discovered, not invented. The Pythagorean theorem was true long before humans existed. Prime numbers existed long before we identified them. Math is something that is external to all of us. It has properties that we can explore but do not create. And here is where this idea connects to simulation theory. If the universe is mathematics, then it is fundamentally computational. Mathematics itself is just a form of computation. Running equations is exactly what computers are designed to do. Our universe could be a mathematical structure that is being computed. The computation would then generate our experienced reality. It would generate it as the output of the system. Physicist John Wheeler proposed a similar idea decades ago. He said that information is the true foundation of reality. Not matter, not energy, but just pure information. He coined the famous phrase "it from bit" to describe this. Everything that is physical emerges from information processing. But Tegmark goes even further than this idea. He proposes that only certain mathematical structures can exist physically, specifically structures that are computable and decidable. This is in the sense of Gödel's incompleteness theorems. This would place an upper limit on the complexity of the universe. Only mathematical structures that are simple enough to be calculated, only those can become real universes in the multiverse. This would explain why our universe seems to follow simple laws, why physicists keep finding such elegant equations. why nature always seems to take the computational shortcuts. If the universe were truly arbitrary, its laws could be infinitely complex. Instead, we find symmetries, conservation laws, and principles. Principles like the principle of least action in physics. All of these are forms of compression techniques, ways to generate the maximum complexity from the minimum rules. Critics argue that Tegmark's hypothesis is completely unfalsifiable. How would you be able to test whether the universe is mathematical? Every experiment that we perform uses mathematics. Every single observation requires a mathematical description. Tegmark says that his hypothesis does make some predictions. It predicts that physics research will continue to find mathematical regularities, that no physical phenomenon will ever be discovered. A phenomenon that cannot be modeled in a mathematical way. So far, this particular prediction has held true. Every new discovery that has been made in physics fits into a framework that is based on mathematics and equations, from the Higgs boson to gravitational waves to quantum entanglement. Nothing in our universe seems to defy mathematics. Some philosophers have rejected the mathematical universe hypothesis. They have rejected it on a matter of principle. They say that it confuses the description with the reality. A map of a territory is not the territory itself. The equation that describes an electron is not the electron itself. But how do you distinguish between the two of them? If the electron has no properties other than mathematical ones, then what exactly is the difference between the two? Spin, charge, and mass are all just numbers in the equations. If you change the numbers, you change the particle. The numbers are what the particle is in essence. This gets even stranger when you consider quantum mechanics. Particles do not have any definite properties until they are measured. Before the measurement, they exist as what are known as wave functions. These are mathematical descriptions of pure probability. If reality is mathematical before observation creates definiteness, then maybe it is just mathematical all the way down. And nowhere is this more obvious than in the fundamental constants. There are no messy or complicated physical laws. Every single force that is found in nature can be described. It can be described by a simple and elegant equation, not an approximation and not a rule of thumb, a perfect and exact mathematical relationship. This should not be a possibility in a random universe. The universe could have been chaotic and completely random. It could have been following no patterns at all. Instead, it obeys all of these mathematical rules. It does so with an absolute and perfect precision. Let us take the force of gravity as an example. Isaac Newton wrote down an equation over 300 years ago. This equation works for every massive object in the universe. You can drop a ball or you can orbit a planet. You can calculate the motion of a galaxy with it. It is always the very same simple equation. Einstein improved upon it with his theory of general relativity, but general relativity is also pure mathematics. The stress-energy tensor equals a set of other mathematical terms. It is beautiful, precise, and completely universal. Why does matter curve space-time according to this exact equation? Why does it not follow some other kind of relationship? Why are there not different rules for different situations? Electromagnetism is another equally elegant theory. Maxwell's 4 equations are able to describe every single phenomenon, every electrical and every magnetic phenomenon in the universe. From lightning to radio waves to the light that is hitting your eyes. Just 4 simple and elegant equations with no exceptions. The strong nuclear force follows the equations of quantum chromodynamics. The weak nuclear force obeys the electroweak theory. Even the newly discovered Higgs field has a precise mathematical description. Nothing in all of nature seems to be able to resist mathematics. This is something that is deeply suspicious to some people. If the universe is made of some kind of physical stuff, why should it care at all about our human equations? Matter could just do whatever it wants to do. Instead, it follows all of these rigid mathematical laws. Unless matter is not the true foundation of our reality, unless mathematics is the foundation, and matter is just one way. One way that the mathematics is able to manifest itself. Physicist Eugene Wigner wrote a famous paper about this. He called it "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." He said that it is a miracle that math works so well, that it works so well for describing our reality. But maybe it is not a miracle at all, maybe it is expected. If reality is just a computation running mathematical structures, then of course every physical law is just an equation. The laws of our universe are literally just lines of code. Symmetry is another important clue in this mystery. Physicists absolutely love the concept of symmetry. This is because it can simplify their complex equations. If a system is symmetric, you can use that symmetry. You can use it to reduce the complexity of the calculations. But here is what is so strange about this. Nature seems to respect every single symmetry that physicists discover. The conservation of energy comes from time symmetry. The conservation of momentum comes from space symmetry. The conservation of charge comes from gauge symmetry. These are not just mere coincidences in our universe. These are deep and profound connections between mathematics and physics, between abstract principles and our concrete reality. Emmy Noether proved in 1915 that every continuous symmetry, it corresponds to a specific conservation law in nature. This is what is known as Noether's theorem in physics. It is one of the most profound results in all of physics. Why should the universe obey Noether's theorem at all? Why should abstract mathematical relationships dictate physical behavior? Perhaps it is because the universe itself is just mathematics. And this gets even more extreme as you look deeper. Quantum field theory describes particles as excitations in some kind of underlying quantum fields. But what exactly is a field in this context? It is just a mathematical function that assigns a value to every single point in all of space-time. There is nothing physical about it, it is just numbers. An electron is just a ripple in the electron field. The numbers at that location in the field are higher than the baseline. That is all that an electron is, just a pattern of numbers. This raises a very uncomfortable question for us. If everything is just mathematical patterns, what is doing the computing? What kind of system is running all of these equations? Some physicists say that no computer is actually needed. Mathematical structures just exist independently on their own. They do not need to be calculated by anything at all. They just are in and of themselves a reality. But this seems to be a very unsatisfying explanation. In our own experience, mathematics requires a mind or a machine. It requires something to be able to process it. Equations do not just solve themselves on their own, unless there is something that we are missing about them. Some underlying computational substrate that all mathematical structures inhabit. Or perhaps the universe is self-computing in some way. It is processing its own equations in real time. Each moment is calculating the next moment using physical laws, using the physical laws as a set of algorithms. This is what is known as the loop theory of reality. Reality is emerging from its own ongoing computation. There is no external processor that is running the show. The universe is both the code and the machine that is running the code. Physicist Stephen Wolfram has proposed a related idea. He says that the universe is a kind of cellular automaton, a very simple computational system that is following basic rules. Complex behavior is emerging from simple starting conditions. He has shown that very simple cellular automata can generate complex patterns. Patterns that look just like the physics that we see. They look like space-time and they look like quantum mechanics. If Wolfram is right about this, the entire universe could be running. It could be running on a set of rules that are as simple as a few lines of code. And maybe that code has its own fingerprints, signatures that could reveal its digital and artificial nature. What if space-time itself actually has its own pixels? This is the central and most important question of digital physics. It proposes that the universe is not infinitely smooth. Instead, it is a discrete and quantized system. It is made of tiny, indivisible units, just like a computer screen. From a distance, it looks like it is continuous. But if you look up close, you can see the individual pixels. The resolution of reality would be finite in this case. Several different theories in physics point toward this. Quantum mechanics already assumes that energy levels are discrete. Electrons are known to orbit atoms at very specific distances. They do not exist in between those allowed distances. They can jump from one orbit to another without passing through the space. This is the concept of quantization in physics. Reality seems to come in discrete and finite chunks, but the field of digital physics goes even further than this. It suggests that space itself is also quantized. There is a smallest possible distance called the Planck length. It is about 10 to the power of minus 35 meters. Below this incredibly small scale, the concept of distance breaks down. Space-time would become grainy, foamy, and discrete. This is not a proven fact, but multiple approaches to quantum gravity predict it. String theory, loop quantum gravity, and causal set theory. All of them require space-time to be fundamentally discrete. It must be discrete at the very smallest of scales. If this is true, it means that the universe has a resolution limit. Just like a video game engine, the smallest unit of space is 1 Planck length. The smallest unit of time is 1 Planck time. This is about 10 to the power of minus 44 seconds. Nothing in the universe can be smaller than this. Reality itself would be pixelated at its core. Physicist Konrad Zuse proposed in 1969 that the universe is a computer, a digital computer that is running a simulation of itself. He suggested that it runs on cellular automaton rules. It would be processing reality one single step at a time. Nobody took him seriously at the time that he proposed this. Now the idea is becoming much more mainstream. Digital physics does face some very significant challenges. Most of our physical theories assume that there are continuous symmetries. Rotational symmetry means the laws of physics are the same regardless of the orientation that you are in. Translational symmetry means they are the same at every location. But a pixelated universe would break these symmetries. If space is a grid, there would be preferred directions. Horizontal and vertical would be different from the diagonal. We have observed no such preference in our universe. The universe appears to be perfectly symmetric to us. Advocates of digital physics have a response to this. They say, the pixel size is so small we cannot detect the asymmetries, but at high enough energies we should see violations. Violations of what is known as Lorentz symmetry. Particles would be moving at different speeds depending on their direction. Experiments are currently searching for these violations. They are looking at ultra-high energy cosmic rays, particles from space that are hitting the Earth with enormous energy. If space-time is discrete, these particles should show directional preferences. So far, no violations have been found in the data, but the search for them continues with more sensitive instruments. Another prediction of digital physics involves information limits. If the universe is computational, it has finite processing power. This means there is a maximum amount of information that can exist, a maximum amount in any given region of space. This is already suggested by black hole thermodynamics. The amount of information in a black hole is proportional to its surface area. It is not proportional to its volume as you would expect, a two-dimensional limit on a three-dimensional space. This is exactly what you would expect from a holographic simulation, a simulation that is running on some finite hardware. Some scientists have proposed some tests for this idea. If the universe is digital, certain quantum effects should behave differently. Particles should decohere much faster in systems that are near the information limit. Gravitational wave detectors might be sensitive enough to detect this. They might be able to detect the granularity in space-time. If space has pixels, gravitational waves should show tiny irregularities, a kind of static in the signal that we receive. The G0600 detector in Germany has detected unusual noise patterns. Some researchers have interpreted this as evidence of holographic noise. The grainy texture of reality is showing through. This interpretation is very controversial and not widely accepted, but it is being studied very seriously by some physicists. Stephen Wolfram has been developing his own physics project, an attempt to derive all of physics from simple computational rules. He has published models that can generate relativity and quantum mechanics. They can do so from networks of discrete elements. His approach treats space as a kind of graph, points that are connected by a set of edges. The rules of the system determine how these connections change over time. From these very simple rules, space-time geometry can emerge. He claims that his models are able to produce particles. They can also produce forces and even hints of quantum mechanics. Critics say that his models are far too flexible. You can make them produce almost anything that you want. You can do so by just adjusting the rules of the system. But the core idea of his project remains very intriguing. What if reality is just computation all the way down? What if the entire universe is just software running on some hardware that we are not able to see or detect? And what if we have found direct evidence of this simulation? Something that should not exist in an organic, natural universe. That evidence might already be here with us right now. In Germany, there is a machine that was built to detect the faintest vibrations in the fabric of space-time itself. It is called the G0600 gravitational wave detector. It is so sensitive that it can measure incredibly small distortions that are smaller than the width of an atomic nucleus. Scientists use it to observe black holes that are colliding billions of light years away from our planet. But they have also found something else in the data, something that nobody at all had expected to find. They have found a strange and persistent noise in the detector. Not ordinary noise from mechanical vibrations or electrical interference, but a very specific pattern of noise in the data. A grainy kind of static that should not be there at all. It is like the universe itself is pixelated at its core. And the detector is sensitive enough to be able to see those pixels. Craig Hogan at the Fermilab Particle Physics Laboratory studied these signals. He has proposed that this could be what is known as holographic noise. The fundamental graininess of space-time is showing up in our measurements. Here is how this idea is supposed to work. If the universe is a holographic projection from a two-dimensional surface, then the information in the universe has its own limits. The Planck scale is what sets the minimum resolution of reality. Below that scale, space and time become uncertain. This uncertainty would then appear as random fluctuations. It would be like the static on an old television screen. Gravitational wave detectors are precise enough to potentially see these. The G0600 detector has detected unexpected noise. It has detected it in exactly the frequency range that holographic models predict, not just everywhere and not just random noise, but in specific patterns that match the theoretical predictions. This is a very controversial idea among physicists. Many of them argue that the noise has mundane explanations. It could be seismic activity or temperature fluctuations. It could also be some kind of laser instability in the detector. The detector is incredibly sensitive to its environment. Many different things could be causing spurious signals, but Hogan and his colleagues have ruled out the conventional sources. They have analyzed all of the data very carefully. The strange noise persists even after accounting for all known interference. If this is indeed holographic noise, it means we are seeing the resolution limit of our own reality, the universe. The universe is not infinitely smooth as we once thought. It has a grain structure just like zooming into a photograph. You zoom in until you can see the individual pixels. Other experiments are now testing this very same idea. The holometer at Fermilab was specifically designed to detect this. It was designed to detect the presence of holographic noise. It uses laser interferometry to measure the space-time fluctuations. It does so at the incredibly small Planck scale. The initial results from this experiment were inconclusive. The detector did not find the specific signature that the researchers expected. But this does not disprove the idea of holographic noise. It only rules out certain specific models of it. The search for this noise continues with more sensitive instruments. LIGO is the Laser Interferometer Gravitational Wave Observatory. It has also looked for any anomalies in its data. So far, nothing definitive has been found by LIGO. But here is what makes this so incredibly important. If holographic noise is real, it proves that space-time is not fundamental. Space and time would just be emergent properties of some underlying information. Reality would be discrete, and discreteness is the signature of computation. Every computer in the world operates on discrete values. Bits, which are just ones and zeros, are the foundation. Continuous values must be approximated using a finite precision. This is known to create what are known as rounding errors, tiny discrepancies that can accumulate over many calculations. If the universe is a simulation, it would show similar artifacts, places where the approximation begins to break down, where the discrete nature of the computation becomes visible. Scientists have proposed looking for these artifacts in cosmic rays, high-energy particles that are coming from deep space. If space-time is pixelated, particles that are moving near the speed of light, they should show some directional preferences in their motion. Certain angles would be slightly favored over other angles. This has not been observed yet in any of our experiments, but the energy range that has been tested so far may not be high enough. Ultra-high energy cosmic rays are the most energetic particles that have ever been detected, but they are also extremely rare to find. More data is needed to test this particular idea. Another place to look is in the cosmic microwave background, the ancient afterglow of the Big Bang itself. It shows very small temperature variations across the sky. These variations contain a great deal of information about what the early universe was like. Some of the patterns that are in this data are unexpected. They are anomalies that do not fit our standard cosmological models. There are cold spots, alignments, and statistical irregularities. Most cosmologists think that these are just random fluctuations. They are nothing special to be concerned about. But a few researchers have argued that they could be signatures of some underlying computational structure. If the universe is running on some kind of a grid, there should be preferred directions in space itself. The cosmic microwave background might be able to reveal these preferences. It would do so as subtle asymmetries in the data. Some studies have found some hints of this, but nothing definitive, nothing that cannot also be explained by pure chance. But it is enough to keep the question open for now. The truth is that we do not yet have the technology to definitively test whether space-time is discrete. Our current instruments are very close to being able to, within perhaps 1 or 2 orders of magnitude of the sensitivity. In the next decade, new detectors will be coming online. More sensitive gravitational wave observatories are being built. Better cosmic ray telescopes are also being constructed, and improved measurements of the cosmic microwave background are being made. If holographic noise is a real phenomenon in our universe, we will be able to find it very soon with these new instruments. And if we do find it, then everything that we thought we knew will change. The cosmic microwave background is the oldest light in the universe. It comes from 380,000 years after the Big Bang. Before that time, the universe was too hot for light to travel freely. Then it cooled enough for atoms to be able to form, and for photons to be able to escape into space. Those ancient photons have been traveling through space ever since. We are now able to detect them as microwave radiation. This radiation is coming from every direction in the sky. This ancient glow tells us what the early universe was like, and it contains some strange patterns that should not exist. The temperature of this radiation varies slightly across the sky. These are tiny fluctuations in the temperature. These fluctuations are the seeds of all of the structure in the universe, regions that were slightly denser than the average. They became the galaxies that we see today in the universe. Regions that were slightly less dense became the cosmic voids. Standard cosmology predicts that these fluctuations should be random. They should be following a specific statistical distribution, a distribution that is known as a Gaussian random field. And for the most part, they do follow this prediction, but not everywhere and not completely in the data. In 2017, a team of scientists published some evidence that supports the idea of a holographic universe. They analyzed the irregularities in the cosmic microwave background. They did so using some new holographic models that they had developed. The results that they got matched the holographic predictions. They matched just as well as they matched the standard inflation models. This does not prove that the universe is a hologram, but it does show that holographic models are equally valid explanations. Valid explanations for what we are observing in the data. There are also other anomalies that have been found. The cold spot is a region of the sky where the cosmic microwave background, it is significantly colder than what we would expect. It is about 0.00007 degrees Celsius below average, and it spans roughly 5 degrees across the sky. This should be an extremely unlikely thing to find. Random chance predicts that features this large and this cold, they should appear only once in many thousands of universes. Yet here it is in our own universe for us to see. Some researchers have proposed that it could be a supervoid, a massive empty region of space that is between us and the background. Photons that are traveling through this void would lose energy, and they would therefore appear to be colder to us. But surveys of the galaxies in that region do not show a large enough void, so this particular explanation does not seem to work. Another theory suggests that the cold spot could be evidence of a collision with another universe in the past, a bubble universe that has bumped into our own. This is pure speculation, but it is mathematically possible. It is possible in some of the multiverse models, or it could be a computational artifact of some kind, a glitch in the simulation or an error that has propagated through the calculations and left a signature. There are also more anomalies that have been found. The axis of evil is a name that cosmologists have given to an unexpected alignment in the cosmic microwave background. The large-scale temperature patterns seem to line up. They seem to line up with the plane of our own solar system. This should be completely impossible if our models are correct. The cosmic microwave background is coming from the edge of the universe. Events that are happening here should have no correlation with patterns there. The two of them are what is known as causally disconnected. Light has not had enough time to travel between them, not since the moment of the Big Bang itself. Yet this strange alignment exists in the data. Multiple different studies have confirmed its existence. Nobody knows for sure why this is happening. Some scientists have dismissed it as just a coincidence. Others have said that it reveals problems with our cosmological models, and a few have suggested that it indicates something is fundamentally wrong with our understanding of space and time itself. If the universe is a simulation, then preferred directions could emerge. They could emerge from the coordinate system that is used in the code, just like how video game environments often use Cartesian grids that are aligned with the screen that you are looking at. The programmer's choice of coordinates could leave traces in the output of the simulation that we can detect. Subtle traces, but detectable with our instruments. Roger Penrose has also pointed to other anomalies. He has argued that the cosmic microwave background shows more uniformity than the theory of inflation is able to predict. The universe is just too smooth on the largest of scales. This suggests that something other than inflation has shaped the early universe. Penrose has proposed his own theory of conformal cyclic cosmology, the idea that our Big Bang was the end of a previous universe. But this is also a speculative idea that lacks strong evidence. What we know for certain is that the cosmic microwave background has surprises, features that do not fit perfectly into our standard models. Most of them are probably just statistical flukes. They are unusual, but they are not completely impossible. But some of the patterns in the data still persist. The cold spot has not gone away in our new data. The axis of evil remains aligned in our new data. These are confirmed observations that need an explanation. And as our measurements of this background improve, we keep on finding more and more irregularities in it. Smaller anomalies and deviations from perfect randomness. Each one of them could be nothing at all, just noise, or together they could be pointing towards something profound, a message that is hidden in the oldest light that we can see. If that message does exist, we are only just beginning to decode it. A philosopher at Oxford University has proven something disturbing. Not that we are living in a simulation, but that one of three statements must be true about our reality. His name is Nick Bostrom, a well-known philosopher. In 2003, he published a paper that changed how we think. It changed how scientists think about the nature of reality. The argument that he made is completely airtight. It is based on pure logic, and you cannot escape its conclusions. Here are the three possibilities that he has proposed. At least one of these three must be true. First, that civilizations go extinct before they develop the technology that is needed to run realistic simulations. Something always kills every advanced species before they reach that point. War, climate, disaster, or artificial intelligence gone wrong. Whatever the cause, nobody is able to survive long enough. Survive long enough to be able to build ancestor simulations. Second, that advanced civilizations develop the technology, but they choose not to use it for some reason. Either they decide that simulating conscious beings is unethical, or they simply lose interest in doing so over time. Or they are prevented from doing so by some kind of laws. For some reason, nobody ever runs these simulations, even though they have the ability to do so. Third, that we are almost certainly living in a simulation. Living in a simulation right now, at this very moment. Bostrom has proven that these are the only three options, and he has shown that if the first two are false, the third one must be overwhelmingly probable. Here is the logic that he uses in his argument. Assume that civilizations sometimes do survive to become advanced, and assume that some of them do run ancestor simulations, programs that are designed to recreate their evolutionary history, simulations that are detailed enough that the beings inside are conscious. How many of these simulations would they be able to run? Millions of them, or even billions of them? A single advanced civilization could run countless simulations. It could do so using just a tiny fraction of its available resources. Each of these simulations would contain billions of conscious beings that are living out their own simulated lives. Now you can do the math to see the problem here. How many real civilizations are there in the universe? Maybe there are thousands of them across the observable universe. How many simulated civilizations are there in total? Trillions of them, or even quadrillions of them. The number of simulated beings would vastly outnumber the real ones. If you are a conscious being, what is more likely? That you are one of the rare, real, base reality ones, or that you are one of the numerous simulated ones? The odds are in favor of you being in a simulation. They are in favor by an absolutely enormous margin. Bostrom is careful to say, this does not prove that we are in a simulation. It only shows that if simulations are possible, and sometimes created, then most of the conscious beings in existence are simulated. But it does raise the probability of this dramatically. It raises it from something you might dismiss as science fiction to something that you should be taking very seriously. Elon Musk has cited this very argument in the past. He has said that the odds that we are in base reality are 1 in billions. His reasoning for this is quite simple and easy to follow. Video games are already creating believable virtual worlds, and they are improving at an exponential rate over time. In just a few decades, we will have simulations that are indistinguishable from our own reality right now. If we can do this, then other civilizations can also do it, and they probably have already done so many times over. We could just be characters in someone else's video game. Some philosophers have objected to the simulation argument. They say that it assumes far too much about the universe. Maybe advanced civilizations cannot run conscious simulations. Maybe consciousness itself requires a biological substrate. Maybe the computational requirements are fundamentally impossible. But Bostrom only needs the possibility of this to be non-zero. As long as some civilizations are able to run some simulations, the logic of his argument will still follow through. The number of simulated beings will outnumber the real ones. Others have argued that the simulation hypothesis is unfalsifiable. How would you be able to test it if you are inside? Any evidence that you find would exist within the simulation. The simulators could just fake anything that they wanted. This is true, but it does not make the argument invalid. Some true statements cannot be directly tested by us. That does not mean that they are false statements. What makes Bostrom's argument so powerful is its structure. It is what is known as a trilemma with 3 options. One of those 3 options must be true for us. You can argue about which one of them is the most likely, but you cannot just dismiss all 3 of them. Either we are all doomed to go extinct in the future, or advanced civilizations universally choose not to simulate, or we are all currently living inside of a simulation. Personally, I find the first 2 options to be less plausible. I find them to be less plausible than the third one. Civilizations probably do sometimes survive to become advanced. And if simulation technology exists, someone will use it. Our own curiosity alone is enough to drive that. This leaves us with the uncomfortable final conclusion. We are probably simulated beings in a simulated universe, and if we are, there might be ways to detect it, not by finding the simulators themselves, but by finding glitches, finding the limits and the places where the simulation cuts corners. Scientists are already beginning to look for these. Elon Musk does not say things lightly, he calculates. He analyzes the data and he thinks about the probabilities, and when he speaks about the nature of our reality, people listen. At a conference in 2016, Musk made a statement that rippled through the technology and science communities. He said that the odds that we are living in base reality, that those odds are 1 in many billions against it. He did not mean this in a metaphorical way, he meant it literally. The probability that this is real and not simulated, that probability is effectively 0 in his view. His reasoning for this comes from the pace of technological advancement. 40 years ago, our video games were just Pong, just 2 simple rectangles and a single dot on the screen. Now we have photorealistic virtual worlds to explore. Characters with complex behaviors and physics engines that can simulate reality quite convincingly. This incredible improvement has happened in just 4 decades. That is just a blink of an eye in cosmic time. Now, let's extrapolate this trend forward into the future. In another 40 years, our games will be indistinguishable. They will be indistinguishable from our own reality. We will have full immersion virtual worlds and conscious AI, simulations that will feel completely real to everyone inside them. Now let us extend that timeline even further out. Not just 40 years or 100 years, but thousands. Thousands of years or even millions of years. What could a civilization 1 million years more advanced than us create simulations that are perfect in every single detail? universes that are as complex as our own universe, conscious beings who have no idea that they are simulated. And here is the key point of his entire argument. If one advanced civilization is able to create simulations, they will most likely create many of them, not just one. Why would you run just one when you can run millions? Each of these simulations could contain billions of conscious beings. So let us count the number of conscious minds in existence. A few billion humans that are in the base reality, and trillions of simulated humans across millions of simulations. The number of simulated minds would outnumber the real minds. It would do so by factors of millions or billions. You are a conscious being. What are the odds of your situation? The odds that you are one of the rare base reality minds versus one of the numerous simulated minds that exist. The odds are billions to one in favor of you being in a simulation. Musk has also pointed out that progress toward realistic simulation, that this progress is inevitable unless something stops it. Extinction of our species or a technological plateau, or a deliberate choice by us to stop this progress. But extinction seems unlikely for all civilizations. Some of them will most likely survive in the long run. A technological plateau contradicts every trend that we observe. Technology seems to be accelerating, not slowing down, and choosing not to simulate seems implausible to him. Our curiosity as a species is a universal trait. Therefore, simulations will be created in the future. They are being created right now, and they have been created. They have been created countless times already in the past. Other leaders in the tech industry have agreed with him. Many people in Silicon Valley take simulation theory seriously, not as a form of philosophy, but as a matter of probability. Some of them go even further and suggest that we might detect it. If our universe is running on finite computational resources, there should be certain limits, optimizations, and shortcuts. Musk himself has joked that we should hope we never make the simulation. We should hope we never make it too boring for the simulators, or they might just shut the whole thing down. Accelerating technological progress helps to keep things interesting. It gives them a good reason to keep the program running. This also raises some very difficult ethical questions. If we are all simulated, do our experiences truly matter? Are our lives really real in any meaningful sense? Musk would say yes, they are, and they do matter. Consciousness is real regardless of its substrate. Simulated suffering is still a form of suffering. Simulated joy is still a form of joy to be had. The medium in which it exists does not really matter. The experience itself is what is truly real. This also connects to his work on artificial intelligence. If consciousness can exist in silicon as well as in carbon, then there is no fundamental difference between the two, between biological minds and artificial minds. Both are just information processing systems in the end. And if consciousness is substrate independent, then simulated beings are real. They are just as real as the base reality beings. Their lives would have an equal amount of value. But this also means that we have certain responsibilities. If we develop our own simulation technology in the future, we will then become the simulators of new worlds. We will be creating conscious beings in virtual worlds. Those beings would then depend on us for their existence. Shutting down the simulation would be a form of mass murder. Manipulating it for our own purposes would be tyranny. Musk believes that we are already on this path. Neural interfaces and brain-computer connections, virtual reality and artificial intelligence are all a part of this. All of these things are pushing us toward the ability to create simulations. Within this century, we might run our own ancestor simulations. We could create virtual worlds that are populated by conscious AIs. AIs that are experiencing their own simulated histories. And when we do that, we will understand our own situation better. This is because we will be the simulators looking at our simulations, just as our simulators might be looking at us right now. The hierarchy of this could extend indefinitely upwards. Simulations that exist within other simulations. each level creating the next reality as a nested computation. This is not something that is provable just yet, but Musk finds it to be more plausible than the alternative, that we just happen to exist at the exact moment in history, the moment right before simulation technology is perfected, that we are the base reality, the original beings. The odds of this are simply far too low to be believed. It is better to accept what the mathematics seems to imply. We are all probably living inside of a simulation, and if we are not, we will become the simulators ourselves soon. Either way, the question of what is real becomes much more complicated. There is a specific type of simulation that advanced civilizations would run, not games and not just scientific experiments, but history. They would want to simulate their own past to study it. They would want to watch their own species evolve over time. They would want to see how their own ancestors lived. They would want to study the pivotal moments of their history. They would want to run alternative scenarios to see what happens. These are what are known as ancestor simulation. Nick Bostrom has proposed them as the most likely type of simulation, the most likely type for advanced civilizations to create. Here is why they matter so much to this argument. If ancestor simulations are a common thing in the universe, then most of the conscious beings throughout the universe, they are living in recreations of their own species' history. They are not living in the base timeline of their reality, but in one of the countless reruns of that timeline. Think about what this means for us here on Earth. Human beings are a very interesting species to study. We are at a very critical point in our own history. We are facing climate change, artificial intelligence, and nuclear weapons. We are also developing genetic engineering technologies. The decisions that we make right now will determine our future. They will determine the future of our entire species. This is exactly the period that an advanced human civilization, a civilization in the future, would want to study. They would want to run millions of simulations of this time, simulations of the early 21st century on Earth. They would want to test different variables in the simulation. They would want to see which choices lead to our survival and which of them lead to our ultimate extinction. We could be in one of those simulations right now, a detailed recreation of the Earth between 2000 and 2100. Billions of simulated humans living their simulated lives, completely unaware that they are being studied by their descendants. The simulators would already have all of the records. They would know how history actually went in their timeline, but they would want to be able to explore all of the variations. What if a pandemic is handled in a different way? What if a major war does not happen as it did? What if technology develops at a faster or a slower pace? Each of these simulations would tweak the variables slightly. Then the simulators would watch what emerges from the changes. From inside of the simulation, everything feels completely real. We have our own memories, families, and goals. We have our own experiences of pain and of pleasure. Our experiences are genuine to us, even if our substrate is not. And here is something that is even more disturbing. The simulators might be running the same period many times. They could be resetting it and then trying it all over again. You could have already lived this year before in the past. You could have lived it many times with slight variations, but your memories would be reset each and every time. You would have no way of knowing that this was happening. This is the problem of Boltzmann brains applied to simulations. In an infinite multiverse, you are more likely to be a random fluctuation. You are more likely to be that than an ordered observer. In infinite simulations, you are more likely to be in a short-running test. You are more likely to be that than in a complete historical recreation. Unless the simulators prefer to run complete histories, then most of the simulated beings would live full lives. They would live from their birth to their death without any resets. We have no way of knowing which of these scenarios applies to us. Some philosophers have argued that ancestor simulations would be unethical. Creating billions of conscious beings just to study them is questionable. It is especially questionable if those beings are able to suffer. Wars, disease, and natural disasters are all a part of history. Would an enlightened civilization inflict that on simulated people? Maybe they would, if the knowledge that is gained justifies it. Understanding how civilizations are able to survive existential risks. It could save countless real lives in their own timeline. The suffering of the simulated beings might be an acceptable cost. Or maybe the simulators believe that simulated suffering is not real, that only the experiences in the base reality truly matter. This seems wrong to us, but we cannot rule it out. Another possibility is that the ancestor simulations are sanitized. They might sanitize the worst parts of their history. They might run relatively peaceful periods of time. Or they might just skip over the most traumatic events. This would create an idealized version of their history. It would not be a faithful recreation of what happened. If this is true, we should expect our world to be less terrible than what random chance would predict. Maybe we are in a curated simulation of some kind, one where the existential catastrophes have been turned down. This is an unfalsifiable form of speculation, of course, but it is still very interesting to consider. What we can say is this: if ancestor simulations exist, we are probably inside of one of them right now. The sheer numbers of them demand this conclusion. Real historical periods can only happen one time, but simulated ones can happen millions of times over. Being in the original base timeline would make us special. It would make us uniquely privileged in the cosmos. The odds are stacked against this being the case. It is better to assume that we are one simulation among many, not the prime reality, but just a copy that is being studied, a copy that is being studied by future versions of ourselves. And if that is true, it changes how we should think about our choices. Maybe the simulators are watching us specifically to see how we handle things, how we handle artificial intelligence or climate change. Our decisions might be teaching them what to avoid in their own timeline in the future. Or maybe all of this is completely wrong in the end. Maybe simulations are completely impossible to create. Maybe consciousness requires something that cannot be reproduced. It cannot be reproduced in a computational way. But every year, our artificial intelligence gets more sophisticated, and every year, our virtual worlds get more realistic. The trend is pointing towards simulation being possible, and if it is possible, then it is probably also probable, and if it is probable, then we are likely already there. Nature is lazy in the most precise mathematical sense. The universe always seems to take the easiest path. This is what is known as the principle of least action. It says that particles that are moving through space, they will follow trajectories that minimize a certain quantity, a quantity that is known in physics as action. Not the distance and not the time, but the action. Action is the integral of the kinetic energy minus the potential energy. This is integrated over a period of time. This is a very specific mathematical quantity, and nature seems to minimize it perfectly every single time. Light will take the path of least time through space. A ball that is thrown through the air will follow the trajectory of least action. Planets will orbit in paths that minimize their action. There are no exceptions to this fundamental rule. But here is the question that this raises for us. Why would the universe care about minimizing anything? Physical objects are not conscious beings at all. They do not calculate the optimal paths for themselves. They just move according to the laws of physics. Yet somehow they always seem to find the minimum action solution. It is like they are solving an optimization problem in real time. This is exactly how computer simulations are known to work. To predict where a particle will be in the future, you have to solve an optimization problem to find the path. Find the path that minimizes the action of the particle. That path is where the particle is going to go. The universe behaves just like a computer running physics calculations. It finds the optimal solutions using the same methods that computer programmers use in their work. Fermat's principle describes this for the behavior of light. Light that is traveling through different materials will bend. It will bend at the interfaces between those materials, water to air, or air to glass, for example. The angle of this bending follows a precise law. Snell's law is what gives the formula for this. But Fermat was able to explain why this happens. Light will always take the path that gets it from point A to point B. It will do so in the least amount of time. It automatically solves an optimization problem that is complex, a problem that would take humans a significant calculation. This happens because the light is exploring all of the paths. It is exploring them all simultaneously as a quantum superposition. Then it interferes with itself to find the best path. The path of least time is where the constructive interference happens. All of the other paths will cancel each other out, but this is a fundamentally computational process. The light is effectively calculating which path is optimal. It is doing so by trying all of them and selecting the result. Quantum mechanics is full of these kinds of shortcuts. The path integral formulation sums over all possible histories, all of the possible histories that a particle could take. Then it assigns probabilities based on which histories interfere in a constructive way. This is a very elegant computational trick in physics. Instead of tracking one single definite path for a particle, you can calculate the contributions from every possible path, and then you can let the mathematics determine the final outcome. Physicist Richard Feynman was the one who developed this formulation. He showed that it produces identical predictions to standard quantum mechanics, but it also reveals something much deeper about how nature works. The universe is not just evolving one state forward in time, it is summing over all of the possibilities at once, and it is selecting the outcomes based on interference patterns. This is what is known as a Monte Carlo simulation, a computational technique that is used in many different fields: weather prediction, finance, and nuclear physics, and it is also used in the field of computer graphics. You cannot calculate the exact answer to a complex problem, so you can sample many of the possibilities and average the results. Nature seems to be doing this on a native level. The conservation laws are another kind of computational shortcut. Energy is conserved and momentum is conserved. Charge is also conserved in all physical interactions. These laws are able to dramatically reduce the complexity of the calculations that are needed. Without the conservation laws, you would need to track every particle. You would have to track them all individually in the system. You would have to calculate all of the forces and update their positions. This would be computationally very expensive to do. With the conservation laws, you know that the total energy at the end, it will equal the total energy at the start of the interaction. This is able to constrain the possibilities and reduce the computation. Symmetries are an even more powerful tool for this. If a system has some kind of rotational symmetry, you can completely ignore its orientation in the calculations. If it has a time symmetry, the laws do not change over time. Each of these symmetries is able to eliminate variables. Emmy Noether proved that every symmetry corresponds to a conservation law. This is not some kind of a coincidence in our universe. Symmetries are a form of computational optimizations. Nature uses them to reduce its processing requirements. The speed of light acts as a kind of a frame rate cap. Nothing in the universe is able to move faster than light. This is what limits how quickly information can propagate. It limits this in a simulation of the universe. This is what prevents errors from accumulating over time. Events that are outside of your light cone cannot affect you yet. This is exactly how distributed computing is designed to work. Separate parts of the system can update independently. They do so until signals are able to reach them. The speed of light is what enforces the causal structure. It is what keeps the entire simulation consistent over time. Some physicists have noticed that quantum mechanics itself is a shortcut. It might be a kind of a compression algorithm in disguise. The wave function of a particle contains less information than a complete classical description would require. Yet it is able to generate all of the observable predictions. This is a very suspicious aspect of the theory. Why would nature use a reduced description of reality? Unless the computational resources are limited in some way. Quantum entanglement lets particles share their information. They can do so without storing it all separately. Two entangled particles are described by just one wave function, not two independent ones, which saves on memory. This is able to halve the memory requirement for the system. If the universe is trying to maximize its own efficiency, all of these different patterns start to make sense. Every shortcut, every symmetry, and every conservation law. All of them are reducing the computational load of the universe. And the reduction that they provide is absolutely enormous. Without all of these efficiencies, simulating even a small region of space, it would be completely impossible for us to do. With them, reality itself becomes something that is computable. The speed of light is 299,792,458 meters per second. Not approximately that speed, but exactly that speed. This value is now defined in our system of units. Nothing in the universe is able to move any faster than this. Not matter, not energy, and not any form of information. This is the universe's absolute and unbreakable speed limit. But why does this particular speed limit even exist? What is it that enforces this speed limit in our reality? Einstein was able to show that the speed of light emerges. It emerges from the very structure of space-time itself. Space and time are not separate and distinct things. They are just dimensions of a four-dimensional continuum. Moving through space also means that you are moving through time. The speed of light is just the conversion factor between them. But this still does not explain why that particular conversion factor. Why is it not faster, or why is it not infinite? One possible answer to this comes from the simulation theory. The speed of light acts just like a frame rate cap. It is what limits how quickly information can propagate. It can propagate through the entire simulated system. In a computer simulation, you cannot process everything. You cannot process everything instantaneously at the same time. The program has to update itself in a series of steps. At each step, the computer calculates the new positions. It does so based on the forces and the velocities. Then it displays the final result on the screen. If objects were able to move arbitrarily fast in the simulation, the entire simulation would completely break down. Particles would be able to teleport across the universe. They would do so before the next frame of the simulation. Causality would become impossible to maintain in such a system, so you would have to set a maximum speed for everything. Nothing can move more than a certain distance per time step. This is what keeps the entire simulation stable over time. It is what prevents information from jumping ahead. The speed of light in our universe could be exactly that. A maximum propagation speed that is set by the simulation's time step. And it is also set by the spatial resolution of the simulation. You can calculate the numbers to see how this works. The Planck length is about 10 to the power of minus 35 meters. The Planck time is about 10 to the power of minus 44 seconds. If you divide them, you will get roughly the speed of light. These are not just coincidental relationships between these numbers. The Planck length and the Planck time are the minimum units. They are the minimum units of space and time in our reality. The speed of light is what connects these two units. This is exactly what you would expect if space-time is a discrete grid. At each time step, the information moves one spatial unit. The ratio of these two is the speed of light, but there is even more to this particular story. The speed of light is also what limits causality in our universe. Events that are outside of your light cone cannot affect you yet. You only need to process all of the interactions within your local region. This is something that dramatically reduces the computational complexity. Instead of calculating every particle in the universe influencing every other, you only need to calculate the local interactions. Distant objects will only become relevant to you. They will do so when their light finally reaches you. This is what is known as the light cone structure of space-time. It is a fundamental part of Einstein's theory of relativity, but it is also a brilliant optimization strategy for a simulation. In massively multiplayer online games, the servers use similar tricks. Your own client only receives the updates about the nearby players. Distant players are just abstracted in some way. They might be shown as simple icons on a map, but they are not fully rendered in all of their detail. This is what keeps the bandwidth of the game manageable. The server cannot send the complete information about every player. It cannot send it to every other player in the game, so it has to restrict the updates to just the local regions. The speed of light does the very same thing for our universe. It partitions our reality into different regions that can be processed independently of each other. Then it integrates them as the information arrives. Quantum mechanics adds yet another layer to all of this. The uncertainty principle prevents you from knowing both position and momentum. You cannot know them both precisely at the same time. This is what limits the information content of the universe. If you could know everything about every single particle, the simulation would need to have an infinite amount of memory, but the uncertainty principle caps the amount of information. Each particle has a finite amount of information content. This is what makes the simulation of the universe possible. The speed of light also explains why time dilation occurs. Moving clocks are known to run slow in our universe. This should not be able to happen if time is absolute. But if time is a part of the simulation's processing, then moving through space means spending fewer updates on the progression of your own time. You would have a fixed computational budget per particle. If you spend more of it on your spatial motion, you would have less of it for your temporal progression. Your own time would then slow down as a result. This is exactly how time dilation works in relativity, and it is exactly how you would implement time. Implement time in a simulation with limited resources. Energy also has to obey a speed limit in our universe. Mass is just energy divided by the speed of light squared. This famous formula connects energy, mass, and the speed of light. Why would these three things be related to each other? In simulation terms, mass is a form of information. Energy is the cost of changing that information. The speed of light is what sets the exchange rate. More massive objects would require more computation to update. Accelerating them would require more energy as a result. The speed of light is what determines how much more. Some researchers have proposed testing whether the speed of light is constant. If space-time is discrete, the speed of light might vary. It might vary slightly depending on the direction, aligned with the grid versus going diagonal to it. So far, no variation has been found in any of our experiments, but the experiments are continuing to improve in their precision. Future measurements might be able to detect tiny anisotropies. If they do, it would strongly suggest that space-time is computational, a grid with some preferred directions in its structure. Even if they do not find anything, the speed of light still looks suspicious. It is too convenient, and it is too perfectly suited to making the universe a computable system. It is like someone has designed it to be that way. We have now arrived at the hardest question in all of science. What exactly is consciousness, and why does it seem to change reality? Why does it seem to change it when it observes it? The double-slit experiment has shown us that observation collapses the wave function. Before a measurement, particles exist in a superposition. After a measurement, they become a definite state. But what exactly counts as a measurement in this context? Does it require a conscious observer to be present? Some interpretations of quantum mechanics say yes. The wave function will only collapse when a conscious observer becomes aware of the result of the measurement. Until then, the particle will remain in its superposition. This is what is called the consciousness causes collapse interpretation. It was a popular idea among the early quantum physicists. Eugene Wigner was a strong advocate for this idea. John von Neumann explored it in a mathematical way, but most of the modern physicists have rejected this view. They argue that any interaction with the environment is enough. It is enough to cause the process of decoherence. Consciousness is not something that is special in this case. A detector, a photon, or even an air molecule, any of these things can be enough to collapse the wave function. This is the mainstream position in physics today, and it is probably the correct one in the end. But it still does not explain why observation matters at all. Why does measuring a particle force it into a definite state? What makes an observation different from any other interaction? The answer to this question might be information. Observation is what creates a permanent record of the state. Before the observation, the particle's state is uncertain, it is ambiguous, and it is not yet defined. After the observation, information exists about its state. This information cannot be erased from the universe. It becomes a part of the universe's own history. And once that information exists, the particle must be consistent. It must be consistent with that information forever. In simulation terms, unobserved particles do not need to be rendered. They can exist just as probability distributions in the memory, potential states that have not yet been calculated. Only when an observation occurs does the simulation need to commit. It needs to commit to a specific value for the state. At that moment, it will run the calculation for it. It will pick a result based on the probability distribution, and it will then update the state of the simulation. This is what is known as lazy evaluation in programming. A programming technique where calculations are delayed. They are delayed until the result is actually needed. This is very efficient for large and complex systems. The universe might be working in the very same way. Most of reality is not being observed at any given moment. Why would you fully calculate all of it at once? You could just store the probability distributions instead, and you could compute the specifics only when they are required. Consciousness becomes relevant because conscious observers create records. They create permanent records of what they have observed. Your brain is able to store memories of your experiences. Those memories contain information about what you have observed. That information cannot be made consistent with the particle being in a different state than what was observed, so the wave function has to collapse at that point. The particle becomes a definite and real thing. The simulation updates itself to reflect this new reality. But this raises a very troubling question for us. If consciousness is what forces reality to become definite, then what existed before consciousness had evolved? Did the universe exist in a superposition for billions of years? Did the first conscious beings retroactively collapse the wave function of the entire past? History of the universe. This is what is known as the Wigner's friend paradox. It is extended to the cosmic scales of the universe. It seems absurd, but some interpretations of quantum mechanics suggest this. John Wheeler proposed the idea of the participatory universe. The idea that observers do not just measure reality, they are actively participating in the creation of it. The universe is not a film that we are just watching. It is a play that we are all starring in together. This might sound mystical, but Wheeler was a serious physicist. He thought that quantum mechanics implied something profound about the relationship between mind and matter. If he is right about this, then consciousness might be fundamental, not something that is just emergent from matter, but something that is fundamental like space and time. This connects to the philosophical idea of panpsychism, the philosophical view that consciousness is a basic property of the entire universe, not just us, not just in humans and in animals, but in everything. Electrons would have a rudimentary form of awareness. Protons would have their own form of experience. Most scientists have dismissed this idea as nonsense, but a few of them are taking it very seriously. Physicist Roger Penrose has proposed that consciousness arises. It arises from quantum processes that are in our neurons, specifically quantum collapses in our microtubules. His theory is very controversial and it lacks strong evidence, but it does suggest that consciousness might be tied to quantum mechanics. It could be tied to it at a very fundamental level. If the simulation theory is correct, then consciousness might be something. It might be the user interface of the entire simulation. The way that information from the simulation is presented to the observers that are inside of it. Your brain would not be generating consciousness in this case. It would just be receiving it like a monitor, displaying output. The output from a computer that is running a program. The computation itself would be happening somewhere else. Your brain would just be rendering the final result. This would explain why consciousness feels so unified, why you experience a single coherent reality, and not just disconnected sensory data from your senses. The simulation is presenting an integrated interface to you. It would also explain the phenomenon of qualia, the subjective experience of redness or the feeling of pain. These are not physical properties of the world. They are how the information is presented to your consciousness. In a simulation, the code does not need to experience anything, but the user of the simulation does need to. So the simulation would include a consciousness interface, an interface that converts the raw data into an experience. We might just be characters in someone else's video game, and consciousness is what makes the game playable. This is a highly speculative idea, but it offers an explanation for why consciousness exists at all, and why it seems to be so connected to quantum mechanics. And it suggests that the hard problem of consciousness, it might be solved by looking outside of physical reality. Quantum mechanics is the most successful theory in all of physics. It is able to predict experimental results with stunning accuracy, to 14 decimal places in some specific cases. No other theory in science is able to come close to this, yet nobody really knows what it actually means. This is what is known as the measurement problem. Quantum mechanics tells us how to calculate all of the probabilities. It does not tell us what happens during a measurement. Why does the wave function of a particle collapse? What determines which of the possible outcomes will occur? The equations of the theory are completely silent on this. Before a measurement, a particle is described by a wave function. This gives the probability of finding the particle in different states. A 50% chance here and a 30% chance there. But when you make a measurement of the particle, you will get one single definite result from it. The wave function will collapse to just a single state. All of the other probabilities will simply vanish. What is it that causes this collapse to happen? The equations of quantum mechanics do not say at all. They only describe how the wave function evolves smoothly. It evolves smoothly over time according to the Schrödinger equation. Then suddenly it jumps discontinuously to one single outcome. This is the measurement problem in quantum mechanics. And after nearly a century, physicists still do not agree. They do not agree on what the answer to it is. The Copenhagen interpretation says that measurement is fundamental. It just happens and you should not ask why it happens. Just calculate the probabilities and then move on. This is a very pragmatic view, but it is also unsatisfying. It treats the process of measurement as a black box, something that is outside of the equations of the theory. This would mean that quantum mechanics is an incomplete theory. The many worlds interpretation is able to eliminate the collapse. It says that the wave function never actually collapses at all. Instead, all of the possible outcomes of the measurement occur. The universe itself splits into different branches. In one of the branches, you will measure the spin to be up. In another branch, you will measure the spin to be down. Both of these outcomes are completely real in this view. You just become different versions of yourself in different branches. This is able to solve the measurement problem by denying something. It denies that measurement is anything special at all. Nothing discontinuous happens to the wave function. The wave function just evolves smoothly over time. It just becomes much more complex as it does so, but the many worlds interpretation has its own problems. It requires an infinite number of universes that are constantly branching, and we can never observe any of these other branches. So this interpretation is completely unfalsifiable. The de Broglie-Bohm theory adds some hidden variables. Particles have definite positions and velocities at all times. We just cannot measure them both precisely at the same time. The wave function guides the particles, but it does not represent probabilities. This is able to restore a sense of realism to the theory. The particles are always somewhere specific in this view, but it does require the presence of non-locality. Particles can instantly affect each other across space, and the hidden variables are undetectable by definition. Objective collapse theories modify the Schrödinger equation. They add new terms that cause a spontaneous collapse. This usually happens when systems exceed a certain size, or when they exceed a certain mass threshold. This makes the collapse a physical process, not dependent on observers. Large objects will automatically have definite properties. Small objects will stay in a state of superposition, but nobody knows what mechanism causes this collapse. And experiments have not yet confirmed the predictions of these theories. Each of these interpretations has its own advantages and disadvantages. None of them are obviously correct to all physicists. Physicists will choose which one they prefer based on their philosophy. But here is what troubles everyone about this problem. The measurement problem should not even exist at all. If quantum mechanics is a complete theory of reality, measurement should be just another physical process, a process that is described by the very same equations, but it is not. Measurement is something special. It seems to follow a completely different set of rules. This suggests that something is missing from our theories, either from our equations or from our understanding of observation. Simulation theory is able to offer a possible answer to this. Measurement is when the simulation commits to a specific value. Before the measurement, the system exists as a probability distribution. It exists as this distribution in the memory of the computer. After the measurement, it becomes a single definite state. This is exactly how Monte Carlo simulations are known to work. You sample from the probability distributions only when you need to, only when you need specific values from the simulation. Otherwise, you just track the distributions themselves. If our universe is being simulated in this way, measurement becomes the moment when the sampling occurs. The wave function is the probability distribution. The collapse is the selection of one single sample. This does not prove the simulation theory is correct, but it does explain why measurement is so special, why it seems to follow a different set of rules. This is because it is a different operation in the code, uploading a quantum state to memory versus sampling from it. Two different functions that are both necessary but distinct. The measurement problem has stalled progress in physics. It has done so for many decades now with no solution. We cannot build a quantum theory of gravity partly because of this, partly because we do not understand what measurement means. If the simulation theory is correct, it might provide the missing insight, not by changing quantum mechanics, but by revealing what it describes. Not the ultimate reality, but the output of a computational process. And the outputs will depend on how you observe them. Scientists are not just speculating about simulation theory. They are actually testing it right now with real experiments. The question is, how can they possibly do this? If we are all inside of a simulation, any test that we run, it would also be a part of that simulation. The results would be a part of the program itself. How do you detect a simulation from the inside? You have to look for the glitches, the limits, and the places. The places where the simulation cuts corners or makes mistakes. Any sufficiently complex program is known to have bugs. If we are able to find the bugs in our reality, we will have found evidence of the simulation. Physicist Silas Bean at the University of Washington proposed a test. He proposed a specific test back in 2012. He suggested looking at the highest energy cosmic rays, particles that are coming from space with extreme energies. If space-time is a discrete lattice like a computational grid, then there should be a maximum energy for these particles. Beyond that energy, the particles would be probing distances that are smaller than the spacing of the grid. The simulation itself would begin to break down. We have not yet observed such a cutoff in the data, but our cosmic ray detectors keep on improving. If this cutoff does exist, we might be able to find it soon. Another test involves looking for correlation patterns. In 2022, physicist Melvin Vopson proposed a test, measuring the information content in different forms of matter. If his second law of infodynamics is correct, then information entropy. It should be decreasing in all of the organized systems. This could be tested by measuring the information content of particles, doing so before and after they have an interaction. If the information is consistently decreasing in these interactions, it would suggest some form of optimization or data compression. Some experiments have also looked for the quantization of time. If time is discrete, then our clocks should show tiny irregularities. This would be especially true for our most precise atomic clocks. So far, nothing has been found in these experiments, but the resolution of our clocks is constantly improving. Next-generation atomic clocks might be sensitive enough to detect Planck-scale time quantization. If this quantization of time actually exists, gravitational wave detectors are able to offer another avenue. The GO600 detector has found some anomalous noise. Other detectors are now searching for similar patterns. If this holographic noise is a real phenomenon, multiple independent detectors should be able to see it. LIGO was recently upgraded to be more sensitive. The sensitivity is now high enough to potentially detect signals from the very early moments of the universe. If the Big Bang itself was a computational event, there might be some signatures of this in the gravitational waves. Quantum computers are able to provide an interesting possibility. If the universe is a quantum computational system, then our own quantum computers might be able to exploit the same shortcuts that nature itself is using. Some researchers are looking for fundamental limits in quantum computation. Places where the mathematics says one thing, but the experiments show another. These discrepancies could reveal the underlying computational architecture. The cosmic microwave background is being mapped with increasing precision. The Planck satellite was able to measure the temperature variations. It did so to a precision of a millionth of a degree. Future missions will be able to improve this even further. If the simulation theory is correct, there might be patterns that we have not yet noticed in the data, symmetries, alignments, and structures that do not fit natural explanations. Machine learning algorithms are now analyzing this data. They are looking for anomalies that human researchers might miss, patterns that only become visible when you analyze millions of data points. Some theoretical physicists are working on making prediction. If we are in a simulation, what should we expect to observe? What would distinguish a simulated reality from a base reality? This is a very hard thing to do, as we only have one universe. We have no control group and we have no comparison, but mathematical models can be used to explore the possibilities. One prediction that they have made is one of simplicity. Simulated universes should have very elegant laws, and they should have very efficient algorithms running them. This seems to match what we observe in our own universe. The physical laws are remarkably simple for the complexity they produce. Another prediction is one of anthropic selection. We should find ourselves in a universe that just barely allows observers. Not a universe that is optimized for life, but not hostile either. This also seems to match the observations that we have made. A third prediction is the presence of cosmological coincidences, the fine-tuned constants and the initial conditions. the universe beginning at the exact moment that complexity becomes possible. All of these are consistent with the simulation theory, but they are also consistent with the multiverse theory, or with the idea of design by a deity or some unknown physical laws. The challenge is to find a test that can distinguish between these, a prediction that is unique to the simulation theory. Some researchers have proposed looking for Easter eggs, jokes that computer programmers are known to hide in their code. Maybe the simulators have left some clues for us deliberately, mathematical constants that are able to encode messages, patterns that are hidden in the distribution of prime numbers, signatures that are hidden in the physical laws themselves. This might sound absurd, but if the simulation is for research, the simulators might want to reveal themselves to us eventually. They are studying us, so maybe they want us to know. No credible evidence for this has emerged just yet, but the search for these kinds of clues continues, and the more that we look, the more questions arise. Let us assume for a moment that we are correct about this, that every single piece of evidence is pointing correctly, that the universe is a hologram, a simulation, or a computation that is running on hardware that we cannot see. What would change for us if this were true? First, death might not be the final end for us. If you are just information in a simulation, that information can be copied, backed up, and restored. The simulators could be able to run you again in a different context, in a different world, or at a different time. You might have already lived before this life, and you might be able to live again in the future. The specific arrangement of the atoms in your body is temporary, but the pattern that makes you who you are could persist. This does not prove that we have immortality, of course. The simulators might just delete everything when the simulation ends, but it does open up possibilities that materialist philosophy denies. Second, the idea of purpose becomes much more plausible. If we are all simulated, then someone has made us. Maybe they have done so for research or for entertainment. Maybe they have done so to solve some kind of problem, but we would exist for a specific reason in this case. We would not be just accidents or random fluctuations. We would not be just meaningless collections of atoms. We would be a part of a designed system that was created, a system that was created with some kind of intention. This does not make our lives any less valuable. It might actually make them even more valuable. Your experiences would matter to whoever is running this. They would care enough to simulate you in the first place. Third, physics would become a code that we could hack. If the natural laws of our universe are just programmed, then they could be exploited by us in some way. Glitches in the code might exist for us to find. Shortcuts that we have not yet been able to discover. Ways to be able to break the rules of the simulation. Advanced civilizations within the simulation might learn something. They might learn how to manipulate the code itself. They could alter the fundamental constants of physics. They could change the physical laws in a local region. They could gain powers that would seem like magic to us, but they would really just be an access to deeper layers of the program that is running our reality. This is all just speculation, of course, for now. But if the universe is computational, then it obeys the rules. It obeys the rules of computation that we know, and all computer systems can be hacked in some way. Fourth, our ethics would become much more complicated. If we develop our own simulation technology in the future, we would then become the creators of new worlds. We would be responsible for the conscious beings we create. Shutting down a simulation that contains conscious minds, it would be a form of mass murder on a huge scale. Manipulating them for our own purposes would be a form of tyranny. We would need to develop new ethical frameworks for dealing with these simulated beings. And if we are simulated, we might owe some obligations to our own simulators in some way, or we might have certain rights that they must respect. The relationship between us is completely unclear. Fifth, the nature of reality would become something that is negotiable. If this universe is just one simulation among many, we could theoretically be able to move to another one. We could escape into a different simulated system. We could find the base reality or create our own universes. Infinite layers of nested simulations could exist, each level creating the next reality in an endless hierarchy. Sixth, the meaning of our lives would shift from survival. It would shift to a form of exploration and discovery, if death is not the final end for us. And if reality is a constructed thing, then the goal of our lives is not just to persist, but it is to discover, to understand, and to experience. We would not be fighting for our survival in an indifferent universe. We would be exploring a designed space, finding the secrets that the creators have hidden for us. Or we would be creating our own meaning in the system. This could be a liberating idea or a terrifying one. It would depend on what the simulators want from us. Seventh, everything that we thought we knew might be wrong. Physics, chemistry, and biology, all of it could be wrong. All of it would just be describing the outputs of a simulation. It would not be describing the ultimate reality itself. We would have been studying the projection instead of the source. The real laws of reality could be completely different. They could be unimaginable to us operating in other dimensions, using a form of mathematics that we have not yet discovered. We might just be children who are playing in a sandbox, learning simplified versions of some deeper truths. Or we might be exactly what we seem to be, conscious beings that are having real experiences, having them in a reality that has been constructed. The medium in which we exist does not really matter. The experience itself is what is truly real. The simulation theory does not diminish our lives. It just reframes them in a different kind of context. You are reading these very words right now at this moment. You are thinking about all of these different ideas. You are having an experience of some kind. That experience is real regardless of its substrate. Simulated suffering is still a form of suffering. Simulated joy is still a form of joy to be had. Love, pain, curiosity, and fear, all of it matters. All of it is a genuine part of our experience. The question is not whether your experiences are real. They are real because you are able to feel them. That is all the realness that is required for them. The question is what they are actually made of, and what that implies about what else is possible. If we are in a simulation, then reality is far stranger than we have ever imagined it to be. But it is also far more hopeful than we thought. This is because information cannot be destroyed. It can only be transformed from one form to another. You might be more permanent than you think you are. You might be more important than you believe you are. You might be a part of a larger story that is still being written. The universe might be a hoax in the sense that it is not what it appears. It is not the fundamental reality, and it is not the deepest layer, but it is not a lie that is being told to us. It is a construction, a work of art, or a system that has been built with a great deal of care, and it has been built with precision and with a purpose. And we are all inside of it trying to understand it. We are pushing at its boundaries and testing its limits. We are asking questions about the nature of our reality. Maybe that is exactly what we are supposed to be doing. Maybe the simulation is designed for beings who wonder, beings who investigate, and who refuse to accept surface explanations. Maybe we are here to discover that we are here. And if we are able to succeed in this endeavor, if we can prove beyond any doubt that our reality is constructed, then we will be faced with the final and most important question. What do we do with that incredible knowledge? Do we rage at our creators, or do we thank them? Do we just ignore them, or do we try to escape? Do we try to meet them, or do we just continue living, learning, and creating our own simulations in turn, becoming the next layer in an infinite tower of reality? The answer to that question will be up to us. This is because even in a simulation, we still make choices. We still have our own agency to act in the world. We still matter in the grand scheme of things. And that ultimately is what makes us real.